Hey everybody, this is chapter 16. In British English, we tend to say simultaneous equations, and in American English, we tend to say systems of equations, but they mean the same thing, and that's what we're going to be looking at in this video. I really like this topic because it's going to have geometry, or I should say graphs at least of lines, and it's going to have algebra, and it's going to have word problems, and it even extends really nicely into higher dimensions, which we all know that I love. So let's get going. So what are simultaneous equations? Well, it's two equations that are happening at the exact same time, and the solution needs to work for both of them. So we couldn't just say, oh, maybe x is equal to 0 and y is equal to 48, because of course that solves the first one. It needs to actually solve both of them. Each individual equation actually has infinitely many solutions, because one equation that has two variables, you can solve it any old way you like. Pick any number for x, and then we could figure out what y would have to be. However, if we have two equations with two variables, that means we should hopefully, not always, but we should be able to solve it in this case. It's good news if the number of equations matches the number of variables. It's terrible news if we have more variables than we have equations. That means we can't do anything. It's actually really nice if we have fewer variables than equations, although that's not going to happen too often. So now we're going to see a couple different ways for how we might want to solve these. So the first is a geometrical way. So we could graph both of those equations because they were both lines, right? So we could graph both of those lines on the same set of axes, and now if the two lines intersect, that's great. We have our one special solution. However, we know that there are special types of lines. Well, it's actually a few different types of special line varieties. We're not interested in perpendicular lines in this particular topic. Perpendicular lines are just two lines that intersect, so that's just this first case. However, parallel lines, we know that parallel lines do not intersect, so in that case, we would have no solution to our system of equations. The two lines in our system, they never meet, so there's no solution. And we've seen what equations like that should look like before. And then our third special case, we've talked about this previously as well, we call them coincident lines. It means they're two lines that are actually the same exact line. They actually fall one right on top of the other. And in that case, there should be infinitely many solutions. Now, I'm saying that we saw this before. Back in chapter 5, we saw how to solve one single equation that had infinitely many solutions or no solution. And we saw how to identify whether it would be in one of those two particular cases. I know here we're dealing with two equations, but as you'll see in a minute, we can quickly take two equations and make them into one. And your other option, of course, is to use your graphing calculator. But remember that for at least most calculators that I can think of, if an equation was written out in standard form, for example, you're going to need to rearrange it, as you saw back in chapter 15, and make y the subject. So just get y alone. So here's an example. If we wanted to solve these two graphically. I feel very confident these two are going to intersect because when I think about the two lines, they have different slopes, right? One is a slope of +2, the other is a slope of -3. They've got to touch somewhere. So really easily, if I had graph paper, I could graph these two, and then I could look, say, hey, where do they meet? Well, they meet at 2, 5. So that means that the x value is 2 and the y value is 5. And your answer must have both components to it to be judged as completely correct. On the calculator, I think we've seen this before, we could just graph both of the equations, and then we're going to go to menu, we're going to analyze this graph, we're going to find the intersection. Here is a left bound, it is to the left of the intersection. I click enter, here is a right bound, it's to the right of it, and there's our answer, 2, 5. Okay, but working with graph paper is tedious, and if the answer wasn't going to be a whole number, then we'd have to really estimate it. Obviously, the calculator can get us a nice decimal approximation, but I don't know, maybe we don't have a calculator handy. Maybe we aren't allowed to use the calculator. There's going to be other ways that we need to know, and they're algebraic ones. So for this first one, this isn't even an official method, but just if we have something easy like this, where we have y as the subject of both equations, then what we can do is we can say, hey, if y is equal to x plus 1 and y is equal to 2x minus 3, then that means that those should both be equal to each other. And so we just set x plus 1 equal to 2x minus 3, and then we solve from there. We're going to get an x value out from that, and then we're going to put that back into either one of the original two equations. It doesn't matter which one, and we're going to get a y value out. Ideally, you would put that x value into both equations to check to make sure, do I get the same y value for both? If you don't, then you've made an error someplace, and you're going to want to figure that out. Now, this is what I meant before when I said we can take two equations and make them one. I know from looking at this that we're going to have one and only one solution, because on the left I have 1x and on the right I have 2x. I'm going to run into problems when I have, for example, 2x on both sides. That would indicate that we have either no solution or infinitely many solutions. And again, we could think about that in terms of slopes if we're looking at the equations in linear form there. Let us look at one more here really quickly. We want to solve these two. Again, we have y as the subject for both equations, so we just set 2x plus 5 equal to negative x minus 1. I know there's going to be one solution to this because it's 2x and negative 1x. Great. So we're just going to, combine like terms, do whatever we got to do algebraically. We get an x value out. Awesome. Substitute that back in, and we should get a y value out too. Great. Now, why do I say that this isn't like an official method for solving these? Well, because these examples are really simple. If it's given to us as y equals and y equals right away, there's barely anything to these problems. We're going to now see two more advanced algebraic techniques to be used on more complicated questions. And what you'll see is that what we did in these two previous examples actually could be considered to be either one of the two following techniques. So here's what you really need to know. First one is substitution. So in substitution, we're going to take one equation, which is going to have one of the variables as its subject. In this example, we have y as the subject. Okay, great. And we're then going to substitute into the other one. So in the second equation, instead of writing y, I'm going to write 9 minus x. So I'm substituting 9 minus x into there. And then it's easy because it's just 2x plus 3 times 9 minus x equals 21. And then that's a really easy equation to solve. So we solve that. We get an x value. And then we substitute that back in to get a y value. And we're done. So you could certainly consider a problem like this to be substitution. Since I have y equals 2x plus 5 here, I'm just going to substitute. Instead of y in the second equation, I'm going to write 2x plus 5. So technically, this is substitution. Sometimes it's easier to get x alone, or one of your equations might already have x as its subject. In that case, we're just going to substitute in for x. So we'll put 1 plus 8y into that first equation, and then we're going to solve an equation in terms of y. That's great. We should easily be able to get that as our y value, and then put that back in to either or both of the original equations to get an answer for x and y. Cool. Of course, it's not always easy to get one of the variables alone. Sometimes it's actually pretty annoying to do that. You might have to end up dealing with a bunch of fractions and other stuff. Or maybe the problem is just set up so that it would be faster to do it another way. So here I'm going to show you the third technique, which is called elimination. It's called elimination because we are going to eliminate one of the variables. Now, I know you eliminate one of them in substitution also, so I don't know that this is the best name, but whatever, it's what it's called. I didn't come up with this. So the key for this, though, is that, first of all, we want to have the equations be written in the exact same order. It doesn't say that here in the book, but you really do need that. So in these two equations, you'll see it's the x term and then the y term and then equals and then some real number over there on the right. It doesn't need to be in that specific order, but both of the equations need to be in the same order as each other. And then what we're going to look for is to have the coefficient of one of the variables be the exact same, but, well, they say it needs to be opposite in sign. Truthfully, it could be the same sign. We can just fix that in a second. And then we're going to add the entire equations together, which is simple enough to do, but not necessarily obvious as to why we're allowed to just add equations together. It seems kind of strange idea at first, but just trust me, it's totally fine. I promise. Would I lie to you? Probably. But I'm not lying to you now. Or am I? No, I'm not. Anyway, the effect here is that we're going to eliminate one of the variables because the coefficients had the same size but the opposite sign. So if we had like 5x and negative 5x and then we added them together, then the x would be eliminated. Now, I said I don't care if it's the opposite sign or not because if it's the same sign, you know what we're going to do? We're going to subtract one equation from the other, and that has the exact same effect. So here, you know, I could make x or y the subject of one of the equations. I'm mathematically capable of doing that, but it's not going to be pretty. Like I said before, I'm going to have fractions, and it's going to be annoying to do. So instead of doing that, I'm going to go with elimination. And I notice I'm already set up because I have positive 4y and negative 4y. So I'm going to add the two equations together vertically. 3x and 5x is going to give me 8x, 10 and 6 is going to give me 16. That's really easy to solve for x. X equal to 2. And then substitute it back in. You'll get an answer for y. Elimination's great. If you have something like this, you're going to have to work just a little bit more. Again, I don't want to substitute. None of the coefficients match, but we can make them match. And it'll be your choice. It doesn't matter whether we choose x or y in this case. The book's going to choose to eliminate the x's. So we're going to multiply both equations by some constant. Usually it's the constant of the other coefficient. So what I mean is this first one's 3x, so we're going to multiply the entire second equation by 3. That's a 4x, so we're going to multiply the entire first equation by 4. Or I suppose in this example, they multiply the entire second equation by negative 3 because they really want to have opposite signs. Again, I would have just subtracted and then I would get the exact same result. Now, you don't always have to multiply both equations. Sometimes you only have to multiply one of them and then you're good to go. In fact, we could have, in this case, multiplied, for example, the entire first equation by 4/3. You could imagine distributing that through, and we'd see that this first term would have turned into just 4x. The problem with doing that is that the rest of them then are going to have fractions. So I don't really like doing it that way. I'd rather multiply them both in that case. Although had this been 2x, for example, then clearly I'll just multiply the first equation by 2, and then I'll have 4x, and we'll be good to go. Anyway, just to get to the end of the problem here, we're going to cancel those x's by adding the two equations together. And this one actually ends up being really nice because we have 16 minus 15y. So we just have an answer for y right away. And we can quickly get an answer for x as well. And so now you can see why technically solving a question like this is kind of like elimination also, because if I write my equations vertically and then I subtract this entire equation from the first one, the y's are going to cancel. I'm going to have 2x minus negative x, that's 3x, and 5 minus negative 1 is 6. And then from there, I'm just going to solve for x. And again, I'm going to get x is equal to negative 2, and I'll get the same y value out. So again, those first couple of examples were just really easy ones that could have been considered substitution or elimination. And the final section of the chapter is about word problems. And as always, I'm not going to show you any because every single problem is different. But they're all going to follow these basic steps. So we're going to have a bunch of information thrown at us. We're going to read through it. We're going to think. We're not going to panic. We're going to figure out what are the two unknown quantities in the question. What are we trying to figure out here. And we're going to assign variables to them. I don't really care if you use x and y. I usually use a letter that is like the beginning of the word of whatever it is I'm trying to find out. But it is important that you make a note for what each variable represents. Let x equal the number of cows on the farm, or let c represent the number of cows on the farm. Whatever you want to use, make sure that you know what it is, and more importantly, make sure that anybody reading your work knows what the variables represent. Especially if you're just using the generic old x and y, the reader would have no idea what you were talking about if it was in some, real world context, unless it was about, I don't know, xylophones and yellowfin tuna. Anyway, so we're going to write down two equations, right, that have to do with x and y, and we're going to solve them. Awesome. We've seen a bunch of methods so far for how to do that. We should always check our solutions, meaning you want to check to make sure that they satisfy both of the equations, because if you make one mistake, you might not realize it, because you might get an answer that works for one of them, and you could feel really good about that, but if it doesn't work for the other, then it's not correct. Now you're going to need to decide when you're working, what is the most efficient method for you to solve this thing? Is it set up to use substitution really well? Like, is one of the variables alone in one of the equations? Or could you make it be the subject of that equation really, really easily? Well, in that case, then you should use substitution. Are the variables stacked over one another? Are the equations written in the exact same format? And can you easily make the coefficients for one of the variables match in both equations? In that case, go for elimination. Or if things are just terrible, then you might need to just go to technology and solve it there. And now I want to show you one other thing you can do on technology, which is really awesome, especially when you get into future mathematics courses. So this is from the main calculator screen. We're going to go to menu, and this feels like algebra that we're doing. So I'm going to choose that one. Now, if your screen looks different than mine, it's probably because you have or I'm using a CAS calculator. You'll see mine says it right there, CAS. So if yours is a non-CAS, then you only have 3 options here. Just hang on 1 second. I'll talk to you in just a moment. For the rest of you who have a CAS, you'll notice that right down here it says solve system of equations. Choose that. And there's 2 options here. One is solve system of equations, and one is solve system of linear equations. Well, everything we were just looking was linear, so let's just choose that one. And then, well, this is great. How many equations were there in all the problems that we've been dealing with? 2, and 2 is like the default here. What are the variables? X and Y. I'm pretty happy with that. We can press OK. And then we can just type in whatever the equation is that we were asked to solve. I mean, whatever you want it to be. 3x minus 7 equals y, and 6x plus 2y equals 4. I don't know. Press enter, and you're going to get answers. That's your x value, that's your y value. If you had equations with different letters, then you could have changed what variables you were using here, and it would have given you the answer just the same. It's going to give you it in the same order here as you had there. But so if you have a non-CAS, look, go to menu algebra and then just choose system of linear equations, and then it's the same thing as before. So, you're good to go. So what was up with this solve system of equations that are nonlinear? I mean, it looks pretty much the same thing when I go into it. Well, actually, you could just choose this one and you could do it the same way as before. What this does, however, that the non-CAS cannot do is it can solve systems of equations that are nonlinear. So something like this. You'll see that I have a quadratic in one of my equations. No problem. It tells us x is 1 and y is 3, or x is 2 and y is 6. Those go together. X is 1, y is 3 is a partner. x2, y6 is another partner. You'll see that if you try linear solve, whether you're on the CAS or the non-CAS, it can't do it. It doesn't understand. Now, I don't know why the CAS has both of these, whatever, but if you're dealing with a non-CAS calculator, then you cannot solve a a system of equations where both equations are not linear. But of course, you certainly can solve them by hand using substitution and elimination. This is super easy. Look, we've got y as the subject of both, so we can rewrite this as x squared plus 2 equals 3x. Oh, that means we can move the 3x over, and then we have a quadratic equation that we should know how to solve. This is going to factor really nicely, right? It's x minus 2, x minus 1 equals 0, which means that x is equal to either 2 or 1. And then in each of those cases, we figure out, hey, what would the y value be? Well, it's going to either be equal to 6 or equal to 3. And those are the exact same solution pairs that we saw on the calculator earlier. But that's not why I said that this technology tip was super helpful for future math courses. It's because we can start solving more than two equations at the same time here, which you can do by hand as well, but it becomes increasingly more challenging to do so. And if I could borrow your imagination for just one moment, let's think about why we could not use the graphing technique, for example. So if we have two equations, we can graph two lines in two dimensions. If we have three lines with three variables, we can't just graph those on the xy plane. We would need to graph those in three-dimensional space, which we can do. We can use computer software to model that, and we could see that. And we could try to figure out where those three lines intersect, or actually, oh boy, they would actually be three planes intersecting in three-dimensional space. But that's, you can't do that by hand, and that is, you need to have special software to do that. But you can still use either technology, changing that to three variables in x, y, and z, or you can use elimination or substitution to work those out. I think elimination is generally the best way to do it. And if you go on to study mathematics, engineering, even a couple of different science disciplines in university as your major, then of course you're going to take your freshman year probably is this thing called linear algebra, which sounds a lot like what we're doing now, right? We're studying algebra, we're studying lines, except in the college course you end up solving systems of 4, 5, 6, 100 different equations with 100 different variables in them. And you're definitely not going to try to graph those, but you can still use the techniques we saw here. In particular, elimination is very, very helpful. And you can also use technology, although most colleges today tend to be very backwards thinking and don't let you use a lot of technology in your early courses. So it's a whole lot of elimination. And yeah, a couple of other more advanced techniques. But this course, I'm telling you, if it's taught well, this is an amazing class that just sheds light on so much of what you learned in high school in math and science classes at like this really fundamental level, and it's really cool. I was terrible at it when I was in college. I did not have a clue what was going on. Don't think my professor was that great, but in my adult years, I've gone to YouTube and I've gotten a bunch of books and I've self-studied, and I really love this, and I want to take a linear algebra course again now that I know what it's about, because I just think it's so cool. But I sense that I'm rambling on a little bit again, and we're getting a bit beyond what we're all here to talk about today. So I'm going to go now. I've shared with you all that you need to know about systems of equations for this course. Okay, so we've got our three techniques. We've got technology, which has a few different methods within it. We have just graphing on paper, and we have algebraic techniques, both elimination and substitution. We should be able to solve, for right now, we need to be able to solve systems of linear equations. We should also be able to solve systems of nonlinear equations if they end up being quadratic, because we know how to solve quadratic equations. So we can work that into these as well. I won't require anybody to be able to solve systems of 3 equations with 3 variables, but I'm certainly going to throw some of them at you in the class sets to see, who's up for the challenge and the fun of that. Maybe even some 4 by 4 systems. Who knows? Maybe even more. Anyway, that is all for this video. Hope you enjoyed. Hope you learned something.